Recording in progress.
Loud and clear.
Okay. All right. Hopefully everything works out okay. Hi, everybody. My name is Regina Vrikis. So I figured that I go ahead and start by going over some of the kind of how the class is going to run. So yeah. So hopefully everybody has looked at the Canvas site. Up at the top, sort of like that middle under updates and announcements, if I happen to make an error in class or something like that, that's where that's going to be. So rather than send out a gajillion emails because I make a mistake, that's the way that I'll handle that, just so I don't inundate your inbox with a whole bunch of emails that are not necessary. Equations and tables, that will link you to the heat transfer packet, which is either 41 or 46 pages. I can't remember. I think it's 41 page PDF. But that has all the equations and the tables and all the stuff that you'll need for the exams. So we'll talk about how those will run in just a second. And then problem statements will bring you to, well, I'll go ahead and click on it. Hopefully it'll bring up. So you'll see that the class is divided up into 5 units because there are 5 weeks, so it works really nicely there. There'll be a test a week, which, you know, I don't know, love it or hate it, but at least you don't just have like, 2 exams to show what you know. So I'll have five regular exams at the end of each week, and then there will also be a final exam that will be cumulative. So all the exams will be online. So if I go to assignments, you won't see all of these. Some of these won't be visible to you, but what will be visible to you right now is Unit 1 homework. You should be able, yeah. Yeah, you should be able to see that. If you don't, let me know. But Unit 1, you should be able to see, and it's, I don't know, 20 questions, something like that, of multiple choice conceptual questions. Kind of, do you understand the gist of what's going on? And those types of questions you will see on your exam, but they'll be worth 10 points of, the 100 points that your exam is worth. So your exam will have 5 conceptual problems that will be kind of like your homework. So 5 conceptual questions, 2 points apiece, so 10 points. And then there will be 2 kind of work it out problems that you'll have as well that will be more reflective of what we do in lecture. You can see exam 1 is already, well, it's not already published, but it will be. So you'll be able to see that. You'll see that pop up on Friday. I guess as soon as the clock ticks over to midnight, you'll see it. So it'll be open Friday, all day Saturday, and then it'll close Sunday at 11:59. So if you're one of the people that waits until the very last moment, just make sure that you give yourself enough time so that it doesn't close in the middle of you taking the exam, because it will. At the very bottom, you see there's an exam upload. Well, I don't know. Can we see it? Yeah, I think you can. So you can see exam upload and submission example and exam example. So there's 2 assignments with the word example in it. The one that says requires Respondus lockdown browser, shocking, requires the lockdown browser. So probably many of you have used this before, probably most of you. But if you have not, it's not that bad. Just sometime in the next day or two, go ahead and just click on that. It'll say, oh, you haven't downloaded this yet, and it'll prompt you to download it. Basically, it just works like another browser, like I don't know, like Chrome or Safari or whatever. But you'll open that lockdown browser, and then you'll go to the Canvas page to access the exam when you're ready to take it. But that exam example, I would recommend going ahead and going through that, making sure that it works on your computer and that you don't have anything kind of weird going on. Most people are able to figure it out and get things working at home, but if you are unable to, the UNCC library, if you are in the Charlotte area, does have computers with those with the lockdown browser installed. So it is an option, but obviously it would be preferable if you were able to get that working on your computer. So the way that it will work when you take your exam, again, there's some conceptual questions, and then there's 2 work it out problems. The exam example, it's just, you're just going through the motions, seeing how it works. But at the end, just like for the real exam, at the very end, it will prompt you to take a picture of your work. So all you're going to do is you're going to hold up your piece of paper and take a picture, or, and it'll, however many pieces of paper that it took you to write stuff down, you'll take the picture. And although it sounds really redundant to do it twice, once you go through the motion of you take the picture and you close out of the lockdown browser, after you've done that, I do ask that you actually scan your work in as a PDF. I use Adobe Scan on my phone. It works pretty well. If you've got another scanner app that you like, use that. That's fine. Or if you've got an actual physical scanner, use that. It's fine. And then you can upload that to the exam upload and submission example. So it sounds convoluted, but But yeah, the reason that I have that second step is really just for the graders because it's just easier to go through the PDFs as opposed to the individual pictures. But the individual pictures, I can make sure that no work got changed once the camera and the lockdown browser went off. That's all. So again, kind of convoluted, but that's the way we got to do it. So um, when you do take your exam, there will be a link in the question that will allow you to access that heat transfer packet that you got a link that's available on the home page of Canvas. So that 41-page document with your equation sheet and your tables and all that stuff. That way you don't have to print anything out and it's all there for you. So Unit 1 homework is due Thursday. Actually, is it Thursday? What is it? 25th. Yeah, Thursday night. And then what I'll do is Thursday night I'll post, or as soon as I'll have I guess Friday morning I'll post the solutions to those homework problems, that Unit 1 homework check your understanding thing, and that way at least you'll see the answers to those. So okay, I got any questions so far? So we have to upload pictures and a scanned PDF. Yep. Again, redundancy. It's our friend. But yeah, do we have to take a picture or can we scan and upload while on the lockdown browser? I would like that we do. I would like it if you do both. So the problem with the lockdown browser is you can't. Yeah, Wesley, you've had me before, so I presume maybe I had another way that we did it. Yeah, I had another way that we did it, but since Lockdown Browser now added this functionality of being able to take a picture of your work, this is the way that I'm going to go.
So we'll be taking a picture of the work with our webcams. Is that what we're doing on lockdown?
Oh, yeah, okay. At the very end, it'll just prompt you, and there'll be a button that says "Take a picture." Do you have anything else? Take a picture. That kind of thing. Yeah. So no, I'm not planning on releasing practice tests. I mean, the problems that we go over in class should be enough. If you need additional problems, I would encourage you to try looking at the textbook and looking at the extra problems in there. As far as the textbook goes, in the syllabus, I mentioned that I don't really care if you have an older edition or, I mean, I'm using the nomenclature out of the Incorpora. I don't know, but I'm using the nomenclature from that. So if you use another publisher, the nomenclature might be a little bit different. So you might, I don't know, I'd suggest sticking with the same publisher just so it's not unduly confusing. But there are tons of old editions out there, and I have no problem with that. So Andrew asked, is the lowest test grade getting dropped? Yes. And I mentioned in class this morning, I kind of decided at the last minute that yes, I will drop the lowest test grade. And yes, there is a cumulative final. So there's 5 tests and then a cumulative final. If you have an A with all 5 of those tests, not having one dropped, but you have with all of 5 of those, you have an A. So you essentially probably got an A on every single one of those 5 tests, and your homework average is such that calculating with all those 5 tests, not one of them dropped, if you have an A, then you don't need to take the final. Okay, so I just kind of came up with that this morning. So I didn't put that in the syllabus, but I do plan on adding that verbiage to the syllabus. Yeah, so the exams are closed note. Yeah. All right, so I'm looking through, making sure I think I got all everybody's question answered. Yeah, I think I got everybody. If I didn't get yours, say, hey, wait. Yeah, close note, close book. The lectures are recorded. So the Zoom lecture, it's kind of annoying because, as I recall, I believe I have to go in and individually publish the Zoom lecture, after each of our lectures. And I'm going to tell you right now, I'll be really good at it for like 2 days, and then I'll forget. And I don't want you to have to forget. I don't want you to have to depend on me. So the lectures, which are also being concurrently streamed to YouTube, not the Zoom part of it, not your names or anything, but streamed to YouTube, I'm going to have that auto-populate into the whatever unit playlist that we're in. So this one will auto-populate into the Heat Transfer Unit 1 playlist. Can we use the formula sheet on the test like in previous classes? Yes. So the that equation sheet tables, that PDF, when you click on that, the PDF that gives you, go ahead and click on it. That guy right there is going to be available to you. So it's, if you haven't scrolled through it, you know, I mean, so there's a question about if you print the tables, is that allowed? I mean, it's 46 pages. I don't know that you want to print it. Yeah. So I would say no, just use the PDF on there. You'll have access to it. So it, yeah. Okay. Well, let's minimize out there, and let's hopefully everything goes okay over here. All right. So if you have just gotten out of thermodynamics, if you've just gotten finished with Thermo 1 or Thermo 2, then it'll be a little bit annoying because we treat heat transfer a little bit differently. So yeah, I'll say, oh, don't be annoying to me. So thermo versus heat transfer. Okay, so it's different in the way that we treat Q. So in heat transfer, we treat it as a vector. So it has, just like Despicable Me, it has a direction and it has a magnitude. So yeah. So here is a plane wall. So we've got one side at some TH. Yeah, it's good enough. TH, and this is TL. So high temperature, low temperature. And each of those is an isotherm. So that side of the plane, or your annotate. Oh yeah, the annotated notes are posted. They're posted under, I don't know, notes or in-class problems. Yeah, so if you look on the Canvas site, there should be a button that says in-class problems, and it's under Unit 1. Okay, and we've got this side is at a lower temperature. Perfect. All right, so heat is going to flow from what's hotter to what's colder, so it's going to flow like this. Perfect. So there's our Q. And he's going to flow perpendicularly to the isotherm. The isotherm just meaning that all along that plane, it's at a 1 temperature TH. Okay. So let's see what else. Yeah, so it has a direction and it's got a magnitude. In thermo, we didn't really care. I mean, we sort of talked about direction, but really, because you might say, okay, well, here's my system. You got my system, and There we go. And I've got heat leaving the system, and I just really care about, like, is it going into or out of, but not really a direction like in the X direction or the Y direction. And speaking of direction, it's best when you define your coordinate system. It's best if you define your coordinate system. There we go. Such that your heat transfer, your Q, is going in the direction of increasing going in the direction of decreasing. I'm sorry. It's best if you define your coordinate system such that your X is going in the direction of decreasing temperature, because that way your Q, if it's going in the direction of X, of increasing X, it's going to be a positive number. So I mean, you can flip that. You can put it in the direction of increasing temperature. You're just going to calculate a negative Q, which is fine. Nomenclature. Okay, so nomenclature. Well, in thermo, you've had me. We use the Morin and Shapiro text, and so the way that we refer to heat transfer, we say, okay, well, if it's a lowercase q, then it's energy per unit mass. So kilojoules per kilogram. We do talk about heat transfer rate, but maybe we put a capital Q with a dot on top of it to indicate that it's a rate, and that would be kilowatts. All right, perfect. But in this class in heat transfer, we kind of screw it up a little bit because that lowercase q is actually going to be the one that's in kilowatts or watts. So that's slightly annoying, but there you go. So this guy we would refer to as the heat transfer rate. All right, and then this Q double prime, this would be watts per meter squared. And this is just heat flux. So it's Q over the area. The area is the area through which heat transfer is going to flow perpendicularly. Darn it. Yeah. So yeah, this guy right here. So it would be this area. That's the area that we'd be talking about. All right. All right, so let's kind of move on just a little bit. Right. So three modes of heat transfer. All right, so first one is conduction. So conduction occurs in a stationary medium. Could be, usually we're talking about a solid, but it could also be in a stationary fluid, whether that fluid's a gas or a liquid, but a stationary fluid. And the law that we use, so this is that conduction is just, it's due to molecules that are at a higher temperature, and so they have more thermal energy. Well, they're kind of vibrating, and they'll knock into the lower energy molecules next to them, and then they'll transfer their energy that way. So that's conduction. And I'll put this as stationary medium, heat transfer through a stationary medium. And the law that we use, or the equation, the governing equation that we use to calculate the heat transfer rate for conduction is Fourier's law. So Fourier's law, F-O-U-R-I-E-R, Fourier's law. So Fourier's law, we have Q is equal to negative K negative K times area times dt dx. Perfect. So let's talk about each one of those little things. So K is our thermal conductivity. So thermal conductivity. All right. So our thermal conductivity, it's, well, the units K are in, this is going to be in watts per meter Kelvin. You can also put this in watts per meter degrees Celsius. Let's say that your thermal conductivity is 3 watts per meter Kelvin. That's the same as saying it's 3 watts per meter degree Celsius. And the reason is because the per meter Kelvin or per meter degree Celsius, that per Kelvin per degree Celsius, it's per temperature change. And a change of 1 Kelvin and a change in temperature of 1 degree Celsius is exactly the same amount. So, all right, the area again is the area through which that heat transfer flows perpendicularly. And that would be defined along the isotherm. And then that dt dx, this guy right here, so this is our temperature gradient. And if you look at your book in chapter 1, it says, all right, so if we have one-dimensional steady state heat transfer. So if it's steady state, I'll just put SS, steady state. Then that dt dx is just going to be delta t over delta x. So as far as how you define that delta t, the way that I would define that delta t in this case is it would be TL, so the one on the right face, minus TH, the one on the left face. That's how you would define it. And so you can see, since TL is going to be lower than TH, that dt dx, the delta t over delta x, that's going to be a negative number. And of course, you've got a negative in front of that K term in front of your thermal conductivity in Fourier's law. So the units will work out so that you end up getting a positive number. Okay. All right. So I think we're good there. Thermal conductivity, there should be a video on the Unit 1 playlist that talks about thermal conductivity of different substances. It's dependent on the substance. It's dependent on the temperature. Sometimes it could be dependent on what direction you're talking about within the medium. So properties like thermal conductivity could be different in the X direction as opposed to the Y direction or the Z direction. But if that's the case, if it's different within each direction, you would call that anisotropic. But in this class, we're not going to mess with that. You can just say that K is the same in the X, the Y, and the Z direction. So, all right. Okay. Let's look at. I'll put 2 and 3 together. Because we're not going to talk about it quite yet. We'll talk about it shortly. So convection and radiation. All right, so radiation we probably won't get to today, but we definitely will get to convection. Okay. All right, so problem 1, we have a copper plate that is 3 centimeters thick. It's maintained, or one face is maintained at 400 degrees. The other face is maintained at 100. degrees Celsius, what's the heat flux through the plate in megawatts per meter squared. So heat flux would be Q with a little double prime, the one that's in units of watts per meter squared, or in this case, megawatts per meter squared. So it's Q over A. So just kind of pay attention to your units there. All right, so the way that I set my problems up when I solve it, I write given, find, assume, and then the solution, just to kind of keep things all nice and organized there. Okay. All right. So there's one side, there's the other. And as far as like, I think I'm going to pick this side to be the one that's at 400. I'm going to call this T1. He's 400 degrees Celsius. And then this guy, he's going to be T2. And he's 100 degrees Celsius. All right, and so as you can see, there's not really a need, well, as we will see, there's not really a need to put this into Kelvin or anything like that, but we'll see why in just a second. I guess the only other thing I might want to do is define my coordinate system. So here's my X. So this X, I'm just going to call him X, but I could call him L, I guess, but I'll just call him X. This is 3 centimeters, so 0.03 meters. And that's it. So I'm wanting to know the heat flux, and he is going to be flowing perpendicularly through those isotherms. All right, so I do need to look up, well, actually, before I even get there, let's write what I need to find. So I need to find the heat flux. Oops. To find the heat flux. So that's going to be Q with a little double prime. So I'm going to put that here, Q with a little double prime. All right, maybe I'll include what units I want. So megawatts per meter squared. And then here's whatever I want to assume over here. Okay. I don't know what I want to assume, but we'll see in just a second. All right. Let me go ahead and put my solution up here because I suspect I'm not going to need to assume that much. All right. So clearly I've got a copper plate. It's solid. And so I think, well, the mode of transportation, the mode of heat transfer is by conduction. So I'm going to apply Fourier's law. Not too difficult to guess which equation it's going to be since we've only gone over one of those equations. But all right, so I'm going to apply Fourier's law. All right. So I have Q double prime. And remember, Fourier's law was the negative K A dt dx. Well, I'm applying that, and that's equal to Q. This is heat flux. So I won't have that Q because I'll kind of make a note over here. Heat flux would be this Q over area. So I won't have that. So that's a negative K dt dx. One thing that I will do is I will assume that it's steady state. It's also 1D. So if it's steady state 1D, this is negative K delta T over delta X, where that delta T, so this would be X, and then I would have T2 minus T1. Okay, that's what I was going to say. So steady state, kind of self-explanatory. One-dimensional just means that you only have heat transfer in one direction. And here it's pretty obvious that, since you know, since heat transfer needs to take place perpendicularly to isotherms, it's pretty obvious that it's only going to be in that X direction. We will work problems where we have heat transfer in 2 directions, not 3 directions, but 2 directions. So we will get to see how we're going to have to deal with that. All right, so I have everything there. The only thing that I don't have is that K. And so I'm going to look that guy up. So I'm going to look up K for copper. And remember I said that it's temperature dependent. So since it is temperature dependent, we do need to think about what temperature we're going to use. So we're going to use just the average temperature of that plate. Right, so 400 plus 100 divided by 2. So 400 plus 100 divided by 2. So 250 degrees Celsius. Okay, perfect. So let's see. Let's not worry about that quite yet. So if I look at my heat transfer packet, I think it's actually, yeah, it's A1. So yeah, scrolling through lots of equations that we can use. Okay, I'm totally almost there. Okay, here we are. So table A1, thermophysical properties of selected metallic solids. Great. So let's look at those. So I have copper. Great. I'm not going to worry about any of those alloys down there. We'll just say we have pure copper. So you can see that you do have properties given at 300 Kelvin. We're not at 300 Kelvin, but we do have table or properties here for K, watts per meter Kelvin. But you also have it at other temperatures here as well. So we are, what were we? This was 250. So 250 plus 273 Kelvin. So that's 523 Kelvin, I think. So, okay, let's see. So that's going to be between the, oops. There we go. That's going to be between that guy and that guy, isn't it? So between this guy and that guy, I will kind of, let me highlight the other one here just so you can see. So this guy right here, there's a CP value as well, and that's right below it. We don't need it, but I want you to be aware of how they kind of organize that table. So let's go ahead and delete that because we don't need that. It's fine. Okay, so this is an interpolation problem that you'll need to do. If you do the interpolation right, it's going to be between 393 and 379. I end up getting 384. That seems to be within what's reasonable, so 384.4. If you don't remember, or you just never learned how to interpolate for whatever reason, if you look at my YouTube, or, well, I mean, it doesn't matter, but I do have a video on it's my Thermo 1 playlist. It's Unit 1. It's under the Unit 1 playlist, and it's called Interpolation. So if you do need kind of a refresher on how to do that, or what that is, don't be ashamed. Just go and figure it out. Okay, so I end up getting, so at, so at the average temperature, we end up getting a K value of 384.4. Perfect. and that's going to be watts per meter Kelvin. Again, you can put that in watts per meter Kelvin, or you could put it in watts per meter degree Celsius. It doesn't really matter. So this is also the same thing as 384.4 watts per meter degrees Celsius. And so it really is. It's just plug and chug. I end up getting a value of 3.8, 3.84 times 10 to the 6 watts per meter Kelvin, which is the same thing. I'm sorry, not watts per meter Kelvin. That makes no sense. Watts per meter squared. Run it. There we go. Perfect. They did ask for it in megawatts, so I guess I could do that. So that would be just 3.84 megawatts per meter squared. And that's it. And we'll put a happy little bubble around there. Oops. A little angry down there in that lower left-hand corner for some reason. All right. So if you do have a question, you're more than welcome to put something in the chat, or you can, I know there's not, I don't think there's a, I think I disabled the chat on YouTube. I've been burned before because it's open to the public. So yeah, if you do want the opportunity to be able to throw stuff in a chat, you probably do need to tune into Zoom.
Is there a time variable to this, or am I misreading the T?
Is there a time variable?
So like, is that delta temperature?
It's delta temperature, not time.
Gotcha. Thank you.
Mm-hmm. All right. So problem 2, we have the roof of a heated home, and it's a kind of silly because the roof of that heated home, we're going to say it's flat. Okay. We're going to make our life really nice and simple here. Let's go ahead and draw out our ugly roof here. So write it down here. So here's my roof. Go. Clearly not going to be drawn to scale. Probably need to make it not so egregious, but all right. All right. So again, no, it's not drawn to scale, but I'm doing the best I can. So 0.25 meters thick, and then it's 6 meters by 8 meters. So the area, this area right here is, I'm just going to write it out as 48 meters squared. Okay, so 6 meters times 8 meters. It's made of a flat layer of concrete whose, oh yay, they give us the K value. So that K value is 0.8 watts per meter degree Celsius. Again, you can put it in watts per meter Kelvin. All right. The inner and the outer surfaces of the roof are 15 degrees and 4 degrees. So the inner one is the one down here at the bottom. So here's that guy. He's at this temperature. All right, so we'll call him T1. And he's 15 degrees Celsius. And this other one is going to be at 4. Okay. Here's our T2. Okay, 4 degrees Celsius. So I guess, I guess this is going to be, we'll put things in in terms of Y, so that's in the Y direction. Okay, and then we're talking about things, we're looking at a time period of 10 hours. So what we're looking for is we're looking for the Q lost. Okay. So I'm going to put him in blue, and I'm going to call him Q lost. Oops, not cost. was much better. Okay. They don't tell us the units, so it doesn't matter just as long as you put it in units of heat transfer rate. Auto test, I'm usually pretty specific about the units that I want, so I won't make you guess. But all right, and then we want to find, we're just going to call it cost. Okay. And I'm going to highlight electricity cost this much. Okay, great. And then we're looking at 10 hours. Okay, perfect. All right, so that Q lost, it's going to seem pretty obvious, but let's look at it again. Oops. Keep on hitting this little button. All right, so the Q lost, I'm going to redraw my two isotherms, so I'm just kind of looking in the Y direction just to make it easier. But I have this one, I have that face, and I have that face. And so, yes, I do have heat transfer that's going from one isotherm to the other. So this one being T1, this one being T2, and this one, this is Q by conduction, right? We've just been calling it Q, but it's Q by conduction. It's fine. You can just call it Q. But what they've asked is the rate of heat being lost. And it probably seems pretty obvious that those two things are equal to one another. But let's just make sure, let's show how the math really does show us that. So we're going to do an energy balance. So we're going to do energy balances on both control volumes and on control surfaces. So it's the control surface that we're going to use right now, but let's look at the control volume just for a hot second. So for a control volume, we did it on a control volume. So energy balance, this is just our, our first law of thermodynamics, right? But we might write, we could write E dot ST. So this is the rate of energy stored within a medium. This would be analogous when you're thinking about your first law of thermodynamics, the dE dt term. The one that you probably crossed out most of the time because your problems were occurring at steady state. But it's that term right there. So that's the rate of energy stored is equal to the net rate of energy transferred into the system. So E dot in minus E dot out plus another term that we didn't really mess around with in thermodynamics probably, but it's E dot G. So this is the volumetric heat generation rate. So this guy is due to volumetric heat generation. And that would be due to maybe an exothermic or an endothermic chemical reaction occurring within your medium, maybe a nuclear reaction occurring within your medium, or maybe just an electric current being passed through your medium. And then this, yes, EST is ST is actually, this is the rate of energy stored. Both the terms that I added some text with, those both require a volume. This one too, it requires, I mean, it's right there in the name. You've got a volumetric heat generation. So both of those require a volume. So that's for a control volume. You underline that control volume. We also have for an individual surface. A control surface or a surface. So with a control volume, that's a 3-dimensional thing. A surface is 2D, no volume. And so if you do an energy balance on that, you're only left with 2 terms. All it is just what's going in has to go out, because there's no volume to store it in. There's no volume for energy generation to occur within. So all that to say, this happy little, let me put this all in its own little thought bubble. This is all just to say that yes, your first thought of those 2 things on the left-hand side have to be equal. Well, yeah, they are. But isn't it nice that now we've gone through it and we've proved mathematically that that's totally what it is? Okay, so now that we've done that, let's get that Q conduction. Because Q by conduction is something we can handle by with Fourier's law. All right, so this is negative K. I do need an area there, so Ka dt dx. I'm given the K. They did give me that guy. And then they gave me the area, or at least I've got enough information to calculate that area. So 48 meters squared is that as my area. And then the dt dx, remember we do need to assume something to calculate that dt dx at the moment. So steady state, 1-dimensional. If we do that, then we can say that dt dx is just delta t over delta x, and math works out much more nicely. So negative K A delta t over delta x. All right, so let's plug some numbers in here. So I have, oops, and there's a negative, 0.8 watts per meter Kelvin times our area, 48 meters squared. And then we've got our delta t over delta x. So our delta x was the 0.25, 0.25. And then we've got 4 degrees minus 15 degrees Celsius. All right, so we end up getting, you'll calculate in watts, so 1690 watts. Perfect. And we'll put that just seems like it's just ripe for putting in terms of kilowatts. So there we go. Stop that now. Did I put it right there? Can I do that? Oh, look at that. Amazing. Amazing. Oh, no, like that. Okay. And then the next thing that we needed to do was that was part B, needed to see, okay, for 10 hours of operation, it costs 8 cents per kilowatt hour. Okay, so cost. All right, since I need things, I'm just gonna, why did we use 415 and not 15.4? So yeah, when I define that delta T over delta X, the way I phrase it in thermo is I say it's what it is after minus what it is before. So if you think of it, I mean, that doesn't really make sense, you know, after and before, but the way that I think of it is, well, what it is, you know, if you're looking at the direction of that heat transfer vector, here's the temperature before, here it is after, as far as, you know, if you're looking at the direction of which it flows. So I guess it's the delta T would be the temperature, the temperature of the isotherm that the heat transfer vector is flowing towards. Yeah. All right. So we've got 8 cents per kilowatt hour. We're wanting a cost. So I'm going to let the units kind of guide me through how I'm going to calculate it. So clearly I need dollar signs on the top. So not that one. Okay. So 8 cents, €8 per kilowatt hour. We're talking about letting it run for 10 hours or letting it run. We're looking at a process that takes it 10 hours. How's that? And then we've got 1.69 kilowatts. Okay, there we go. So I end up getting $1.35. There we go. And there we go. Yeah, so yeah, absolutely. Yeah, so it doesn't matter whether I could have put that 0.8 talking about this one right here. I could have put him as 0.8 watts per meter degree Celsius. It wouldn't really matter. Okay, so let's move on to the next one. Okay. So nice seeing some of, I mean, I know I'm not seeing your faces, but I'm seeing familiar names. It's nice. All right, so problem 3. So we have the heat flux that is applied to the left face of the plane wall is 20 watts per meter squared. All right, so let's go ahead and put a little figure together here. Stop it. Grr, we have to deactivate this little button that's causing this. All right, so let me draw my plane wall. And when we say plane wall, it's really kind of another way of saying one-dimensional heat transfer, because with a plane wall, here's an isotherm, here's an isotherm, and again, since heat transfer flows perpendicularly between two isotherms, it's only in one direction. If I was looking at the case where, okay, maybe this is not, like the thickness is not so small compared to the direction, maybe in the Z direction or the Y direction, if that were the case. Let's say that, let's say there's an isotherm and there's another isotherm, then you'd have heat transfer in multiple dimensions. So, but this is a plane wall, in which case it's really thin compared to the other dimensions. And so we only have to take into consideration heat transfer in that one direction. All right, so we've got heat flux applied to a plane wall on the left-hand side, 20 watts per meter squared. Okay, so I'm going to put this as like this. All right, so in its heat flux, so I'm going to put 2 little hash marks there. So this is 20 watts per meter squared. Perfect. Thickness of the wall, great. So thickness of the wall is 10 millimeters, so 0.01 meters. Thermal conductivity is 12 watts per meter Kelvin. And I kind of like jumped the gun as far as, like, the left-hand side is red and the right-hand side is blue, but it does go on. The problem statement says it's 50 degrees on the left-hand side and 30 degrees on the right hand. So I'll put this guy, this is T1. Stab it. T1 is 50. T2 is 30. All right. And this is kind of different because they're not asking me to find something like Q. I'll call that Q conduction. They're not asking me to find that. If they were, it would be pretty easy. Or well, I don't know, maybe it would be easy, but they're asking me, do steady state conditions exist? So I'll just put steady state question mark. So instead of just assuming that it's steady state, I'm not going to do that. So let's see. So the only kind of information I might have about whether or not it's steady state or not, what is the subtext for the, sorry, yeah, it's Q, and I'm so sorry because that's pretty bad. Let me make this a little, how's that? Conduction. Yeah. Yeah. All right. So the only information that it might give me something about whether or not it's steady state, remember I kept on saying, okay, well, I'm going to assume it's steady state. So I'm going to say that dt dx is equal to delta t over delta x. So that's what I'm going to do here. So is dt dx equal to delta t over delta x? And if it is, great. That means it's steady state. So, all right. So I know by a surface energy balance, so let's put him over here. So solution. All right. So if I do a surface energy balance, surface energy balance is going to be, well, it has no volume. So there's no E dot ST, no energy stored, no energy, volumetric energy generation within this medium. So if I do an energy balance just on that guy right there, then it's going to give me E dot in is equal to E dot out. This, of course, this guy, these are in terms, these are rate terms. Now, I know that I've got things in terms of flux, and that's fine. It doesn't really matter because the area through which that flux is going is the same for what's going in and what's going out. So I could put this in terms of flux, and it's fine. So that Q flux has to be equal to this Q flux. Okay. So again, this is, yes, it's watts per meter squared, but the per meter squared is the same for both of them. Okay. All right. And I know, so I know this guy is 20 watts, 20? Yes, 20 watts per meter squared, and it has to be equal to that Q conduction. And I know by conduction, Fourier's law tells me that this has got to be negative K dt dx. And so now, okay, now I have to put kind of a question mark because I'm not really sure if those are equal to one another or not. So I have 20 watts per meter squared is equal to negative K. If it's steady state, that negative dt dx, that dt dx is going to be delta t over delta x. Yeah, my color coding is kind of not making sense anymore. So, all right. I'm going to abandon it, I think. I'll just put it all in black. All right. So the delta t over delta x. So it's going to be, I'm going to say what it is after because it makes sense in my head, but it's what it is after minus what it is before. So 30 minus 50. Okay. So 30 degrees minus 50 degrees. And then over the thickness, which is 0.01 meters. Perfect. Okay. And then the K, of course, I think they gave that to us. Yeah, 12 watts per meter Kelvin or 12 watts per meter degree Celsius. Either one. Doesn't matter. But again, seems like we have figured out that they are not equal because this is 24,000 watts per meter squared. So definitely not equal. And so what we can say in this scenario is that nope, it is not steady state. All right. All right. All right, so let's go to the next guy, or almost to the next guy. So I'm going to kind of go back to our three modes of heat transfer. So we have conduction, which we just talked about. So this is heat transfer through a stationary medium, either a solid or, again, it could be a stationary liquid. And this is given by Fourier's law. Convection. So where conduction, you've got a stationary medium. Convection, you've got a moving medium. So you're talking about a flowing fluid, either, again, a liquid or a gas. So let's say we have a plate. Here's our plate. Here we go. And our plate is at some temperature TS. S would be the surface temperature. So I'll put a little arrow. So TS is equal to, I don't know, something. And it's got a surface area, A. And we have a fluid flowing past it. And they're going to be at different temperatures. Because otherwise, then you have no heat transfer. And what are we even doing here? All right, so here's our fluid. And it's at some temperature T infinity, and it's got some convective heat transfer associated with it. So H is our convective heat transfer.
Can you scroll up a bit?
Like this? Up like that?
Yes, thank you.
Okay. All right. So heat transfer coefficient. Don't like. Hold on a second. There, it's better. All right. So that heat transfer coefficient, convective heat transfer coefficient, he's going to be in watts per meter squared Kelvin, or could be, again, watts per meter squared degrees Celsius. It don't matter. If it's 10 watts per meter squared Kelvin, it's going to be 10 watts per meter squared degrees Celsius. It doesn't matter. So there we go. For the time being, this is going to be a parameter that will just be given to you. But in reality, it's not really something that you could just look up in the back of a book, or look up online with I guess any measure of accuracy. It's dependent on the fluid itself, the fluid properties, the flow characteristics, and it's not a trivial thing, and it's going to be something that we'll deal with in Unit 4. Yeah, Unit 4 is when we're going to deal with it. But at least for the first 3 units, for the first 3 weeks, it's just going to be something that's going to be given to us. So, but again, yeah, it's dependent on the fluid itself, its properties, its thermal conductivity, and again, its flow characteristics as well. All right. So I've drawn the fluid in blue, indicating that it's a lower temperature. And so, well, heat is going to be flowing perpendicularly from my isotherm. Probably can't tell, but that's trying to indicate, I hate that, indicate that it's a right angle. Let me, oh, that's awful too. Make them smaller. There we go. How's that? That's better. So my Q, maybe that's better. There we go. So Q is going perpendicularly to the isotherm being the plate itself. Okay. All right, so that, oh, and it would be good if we had an equation for that. So the equation is Newton's law of cooling. Okay. Yeah, I like it when it's a little bit, the writing's a little bit fatter because it's more forgiving of my bad penmanship. So, all right. So Q is equal to H times A times TS minus T infinity. T infinity being the free stream temperature of that fluid, and then TS being the surface of your plate there. And then again, yes, there's radiation. He's coming, but not quite yet. Okay. So let's work a problem. Easy peasy. All right, so problem 4, we have air at 20 degrees. It's blowing over a hot plate at 50 degrees. The hot plate is 50 by 75 centimeters. All right, so the question was, how would we differentiate conduction versus convection? So if it's convection, you're going to have something flowing, right? It'll be pretty obvious. You'll be given a heat transfer coefficient for one. Yeah, and again, you'll have a fluid flowing over whatever isotherm that you were talking about. All right, so all right, so here's our hot plate. All right, pretty terrible. Okay. All right, so hot plate is 50 by 75 centimeters. I don't know. So the area is whatever 0.5 meters times 0.75. Ow. 0.75 meters is, I feel like it was 0.375 if I'm not mistaken. It's 0.375. All right. And then we've got air flowing. Great. Here's our air coming in. Free stream temperature of that air, and we're going to use T infinity. It'll make more sense why we use T infinity when we get to unit 4, but just go with it for now. That's the free stream temperature, the temperature of the air, and it's 20 degrees Celsius. And then our heat transfer coefficient for that air, 25 watts per meter squared Kelvin. Again, if it makes you feel better, this could be written as 25 watts per meter squared degree Celsius, and that would be fine too. And we want to find the rate of heat transfer in BTU per hour. Yeah, normally I'd be like, what? Got English units and we were given SI units, but no, I didn't mess up. I don't know. I mean, there's always the possibility that I did, but let's go with it. We want BTU per hour. So that's what I want to find. And I know it's Q, not flux, right? I know it's Q, not Q double prime, because it's the units are BTU per hour. It's a rate term. So this is going to be BTU per hour. Perfect. Okay. Assume. I don't know. All right. So clearly we've got heat transfer by convection. The reason that it's obvious to us is, well, we can, you know, they did give us a convective heat transfer coefficient, but they also indicated that that air is moving because it's blowing over the hot plate. So yeah, so we have heat transfer by convection. And so we're going to use Newton's law of cooling, easy peasy. So Q by convection is going to be equal to H times area times Ts minus T infinity. I guess I didn't really write Ts, but yeah, it's on there too. So Ts 250 degrees Celsius. It's super easy right now. This is not so bad. It's really just plug and chug at this moment, right? Nice. All right, so 25 watts per meter squared Kelvin. Perfect. And then we have an area of 0.375 meters squared, and then 250 minus 20. All right, so this guy ends up being, well, we'll calculate it in watts, won't we? This will be 2156 watts. Of course, they wanted it in BTU per hour. I wanted it in BTU per hour, so let's convert to BTU per hour. You will, again, have that heat transfer packet available to you for the test. And this does include some conversion factors. So this is page 12. Yeah, just kind of, you have to, I guess, just get used to where things are. There we go. So there's my conversion factor. So 1 watt, 3.4121 BTU per hour. Easy peasy, no problem. No problem. All right, so oops. So I do need to, darn it. Sorry about that. Or are you not? There we go. So 3, stop being annoying, 3.4121 BTU per hour, 1 watt. Perfect. So I've got 7356 BTU per hour. Perfect. Perfect, perfect. All right. Okay. All right. Boy, there's just a wall of text there, isn't there? All right, so you have experienced convection. I mean, there's some grammar problems here. You've experienced convective cooling if you've ever extended your hand out of the window of a moving vehicle or into a flowing water stream. With the surface of your hand at a temperature of 30 degrees, determine the convective heat flux for 2 cases. So I'm going to start actually writing stuff down. So we got 2 cases. Here's case A. I'm not a great artist, and so that's fine. This is going to be the surface of my hand right there. That line right there is the surface of my hand. So the surface of my hand, zoop, TS, is 30 degrees. All right. And I stick my hand out the window and I'm going 35 kilometers per hour. All right. So air is flowing over my hand. And, all right, so I've got a reference to a velocity and then I've got a reference to a temperature. So T infinity is -5 degrees Celsius. We have a convective heat transfer coefficient H of 40 watts per meter squared Kelvin or 40 watts per meter squared degree Celsius. They do give, again, they've given us a velocity, which is fine. I don't really think we need it, but we have it if we need it. So this is the free stream velocity in the x direction u infinity, and this is going to be 35 kilometers per hour. All right, and then we have case B. All right, so case B, again, yep, we got surface of my hand. So here's that, 30 degrees. But we also have, in this case, I've stuck it in a stream of water. So instead of air, I have water. And that water is at 10 degrees, so a little bit warmer. So free stream temperature, 10 degrees. We have a convective heat transfer coefficient of 900 watts per meter squared Kelvin, which is much bigger than that 40 there. So we'll talk about that in a hot second. So 900 watts per meter squared Kelvin or per meter squared degree Celsius. They do give us a free stream velocity in the x direction. Free stream velocity is 0.2 meters per second. All right, and then the question is, which one feels colder? So find which feels colder, case A or case B. So the one that's going to feel colder is the one where heat's flowing away from your hand faster. The one where the heat transfer rate is higher. So yeah. So again, this is the one where Q or Q double prime is the highest. All right, cool. So let's calculate Q for each case. Now I don't have an area, but that's fine. I can calculate heat flux. So for case A, all right. So I'll call him, let's call this QA. There we go. Sort of looks like an A, doesn't it? All right, so this is going to be H times TS minus T infinity, because remember, I don't need an area there because it's heat flux. It's per unit area, so the area has divided on out. All right, so it's just plug and chug there, isn't it? So this is going to be 40 watts per meter squared Kelvin or meter squared degree Celsius times TS, 30 degrees Celsius, minus a negative 5 degrees Celsius, so 35. I end up getting 1,400 watts per meter squared. That's my heat flux for case A. Perfect. And if I wanted to look for case B, same thing. I've just got some different numbers there. No problem. So this ends up being, so H times TS minus T infinity. All right, let's plug the numbers in. Oops, be consistent. I'll write a B there, although it's an uppercase B. Probably should be more consistent and stick with the lowercase, but that's okay. All right. So it's going to be 900 watts per meter squared Kelvin, or meter squared degrees Celsius, if you'd rather write it that way, it doesn't matter. And then my delta T, again, it's less, which, you know, TS 30 degrees, T infinity, free stream temperature is 10. But even with that, that heat transfer coefficient is much, much, much higher. So this ends up being 18,000. Yeah. So which one feels colder is case B. So case B feels colder. And so let's kind of like just kind of look at those numbers up at the top for each case for air versus water. So even though, you know, like a bigger DT, bigger delta T is going to increase your heat transfer rate, increase your heat flux. That makes intuitive sense, right? And it also makes sense when you plug things into Newton's law of cooling, or even when you're talking about convection. Bigger delta T, higher Q. So even though you do have a bigger delta T for case A than you do for case B, you also have, with that free stream velocity, it's, you know, the free stream velocity for the air is going faster than for the water. However, it's the heat transfer coefficient that clearly has the dominating effect here. Again, that H value is something that you do need to calculate, but if we think about the things that it's dependent on, yes, it's dependent on flow characteristics, including that free stream velocity, but it's also dependent on the properties. So one of the properties that it's dependent on is that thermal conductivity. And if you watch that thermal conductivity video, which why wouldn't you? It was fascinating. But if you did watch that, you may recall that if we look at the thermal conductivity of liquids versus, well, of solids versus liquids versus gases, the thermal conductivity for solids is higher than it is for liquids. The thermal conductivity for liquids is typically higher than it is for gases. And so for water, which is at 10 degrees going to be a liquid, you're going to have a higher thermal conductivity than you are for air. So, okay. All right, problem 6. All right, so I will tell you, we will typically, because I'm trying to mirror what we do in the in-person section, and because we do not have to dedicate class time to testing, we will typically get out, we're not going to go to 7. So I don't know if that's good news to you or bad news to you, but it is just the news that I have for you. So this morning, problem 6 was about where we got to. So we're coming up to the end. So typically 6:30 is probably where we're going to end. Again, because we're not dedicating class time to testing, and it's just going to be open for the 3 days on the weekend. So, all right. So, yes, very excited. All right, but I suspect that the movement towards like a complete dinner plan is going to be, I'm going to be starting with the dirty kitchen, I suspect, when I go downstairs, but it's okay. All right, so consider a person standing in a breezy room, which is kept at 20 degrees Celsius. Determine the total rate of heat transfer from a person if the exposed surface area is 1.6 meters squared. All right. So let's see. All right. So here's the person, and I guess the exposed area that is exposed to the elements. The area is, where is it? 1.6. 1.6 meters squared. Excellent. Okay. So I guess we're saying that, you know, their clothing is a perfect insulator, and they get no heat transfer through their clothing. But there you go. And then the surface temperature of their skin, 20 degrees. Excellent. No, that's a lie. That's totally a lie. Just kidding. I see it down below. Their average body temperature is 29 degrees Celsius. Read. But in our breezy room, right, so we've got movement of air, the breezy room, we have a convective heat transfer of 6 watts per meter squared Kelvin, or meter squared degrees Celsius, whichever one you want to do. Free stream temperature is 20 degrees. Yes, perfect. And that heat transfer is going to be coming off of that person perpendicularly to the isotherm that is their skin. Okay, no, it's not flat. That's okay. It's still an isotherm, and so it's going to be coming off perpendicularly. If you open up your, if you look at, well, if you start your homework or you open it up, and by the way, when you open it up, you can, it's not going to submit until you hit submit. If it does, you let me know. But and I could reopen it, but yeah, there should be a question on there about, it'll show different isotherms and the heat transfer, which direction is the heat transfer going. It's always perpendicular to the isotherm, right? Always perpendicular. All right, so in this case, the mode of heat transfer is convection because we've got fluid flow, air flowing. So, okay. So what am I finding? I'm supposed to find the total rate of heat transfer. So rate Q. Let's put this in watts. That's fine. And I don't really think I need to assume anything. All right. So there's heat transfer by conduction, or by convection here. All right. So I'm going to use Newton's law of cooling. So H times A times TS minus T infinity. All right, so easy peasy, 6 watts per meter squared Kelvin times a 1.6 meters squared. Uh-oh, I think my head's gonna be blocking it. And then I've got TS, TS minus T infinity, so that's gonna be a delta T of 9 degrees. So, be great. Perfect. 86.4 watts. Yes, perfect. All right. So next time, make sure that if you haven't done the readings, go ahead and do those readings. Why not? Do yourself a solid. Yes, it's a dry textbook, but it's, you know, maybe it'll complement what we've done in class. Make sure that you at least start that homework, start looking over the questions, and that way if you have questions about it, you can ask questions during lecture. That's okay. Yeah, so next time, I guess, yeah, do readings, do the readings if you haven't, read the readings if you haven't, start your homework. It ain't that bad, I promise. Multiple choice, super easy, shouldn't take you that long. It's worth 5%, pretty easy 5% to earn. And then we will also start talking about radiation, but not too much. I mean, we'll talk about it. We'll talk about the governing equation for the rate of heat transfer via radiation. Yeah, but we won't go too far into it. We'll save that for Unit 5. So there you go. When are your office hours? Perfect. So office hours, I have in-person office hours before the 9:45 class. So 30 minutes beforehand, 9:15 to 9:45. And then I will also have office hours for you guys. I mean, you can come to in-person office hours if you want to, but I plan to have Zoom office hours right before a lecture. So I will actually start those tomorrow. If anybody wants to show up, I'll just be there. So if you have questions, there you go. And I'll put the link for that on the Canvas homepage. I'm also asking, sure, yeah, if you do have questions, I'm going to hang out for a hot second after this, and I'll end the Zoom, or I'll end the YouTube stream. And problem 4, I'll end the YouTube stream, and if you want to hang around and ask a question, you can do that as well. My TAs, we have 2 for this class. They will also have office hours, and I'll post the link for those and the times for those as soon as they get that to me as well. So 30 minutes before this class, you can get me And again, I'll provide the Zoom link on Canvas. Okay, so that's all I've got. If you have questions, you can hang out and ask them afterwards. Otherwise, you shoot me an email. Yeah. All right. Thank you. Thank you. Thank you. Okay.
This is just a quick question. My internet cut out when I asked if it was open book or closed book, because I know that sometimes closed note means open book. Is it closed book as well?
It is, and
Okay.
you won't. It's not that complicated to need a open book.
Okay.
Yeah, as long as you just follow along and lecture, you should be fine.
Alrighty. Thank you.
Mm-hmm.